This video will finish up chapter 5. So we have talked about isomers, and there are two main categories: constitutional isomers and stereoisomers. Constitutional isomers have the same molecular formula, but a different order of connectivity of the atoms, and stereoisomers have the same molecular formula and connectivity, but a different spatial arrangement of atoms. Now, amongst stereoisomers, we can further divide that into two categories: conformational isomers, which interconvert through bond rotations, and we worked with those when we drew Newman projections. And then the other type would be configurational isomers, which can't be interconverted through bond rotations. You actually would have to break bonds and remake them to interconvert configurational isomers. And then there are two types of configurational isomers: enantiomers and diastereomers. Enantiomers are stereoisomers that have the same physical properties, such as boiling point, melting point, and diastereomers have different physical properties. Look at these two cats. Do you think that they are a representation of constitutional isomers or stereoisomers? Well, look at the connectivity of the cat's parts. Its tail is now over here, and this right leg is now where its tail used to be. So that would be a constitutional isomer. Then we have conformational isomers. So look at this dog. Here it's in its stable form, but now it's balancing on one paw. But all it has to do is move around to get back to its stable conformation. So that would be the type of stereoisomer known as a conformational isomer. Now let's look at the right and left hands. These are examples of configurational isomers. So they are non-superimposable, because if you try to place the right hand over the left hand, you can see that the thumbs don't line up. And to get those to line up, you'd actually have to do some gruesome things and reattach parts of the hand in a different way. Consider a cyclohexane with 3 substituents. And let's look at all 3 of these carbons that I've circled in red. They are all chiral because they all have 4 different groups attached. Since we have 3 chiral centers, we can get a total of 2 to the n or 2 to the 3 total stereoisomers. So we can get a total of 8 different stereoisomers. And just look at how they're different. So in this first green box, all of the groups are pointing up on the left, and then all of the groups are pointing down on the right. So the relationship between these two would be mirror images. They're enantiomers. Then if we look at the next set of stereoisomers, you can see again every chiral center is inverted, and so those two are enantiomers. And the same is true for all of these pairs, and then you add them up and you get to the number 8. But then the question is, what is the relationship between the molecules in the top box and the molecule in this bottom box? That relationship is that they are diastereomers. So diastereomers are stereoisomers that are not mirror images. And you can think of this as a family where there are 4 pairs of twins for a total of 8 kids, but each kid has 7 siblings, where one of the siblings is their twin and the other 6 are diastereomers. So for example, if I'm looking at this compound, this is its twin, this is its enantiomer, but then the rest of the 6 are related to this as diastereomers. So notice here that we've got 2 of the chiral centers in the same configuration, but one is flipped. So with diastereomers, you'll have 1 chiral center the same and 1 chiral center different, and then depending on how many additional chiral centers you have, they could be the same or different. And the maximum number of stereoisomers for a given compound is 2 to the n, where n is the number of chiral centers. So can you figure out the maximum number of possible stereoisomers for this compound cholesterol? So first you have to find all of the chiral centers. So here's one, 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 here's one. And if you're not sure, you can always add in all of your H's, because carbons with 2 or 3 H's, carbons that are sp2 hybridized, those won't be chiral centers. And then there's also a hydrogen here and here. So I've got 1, 2, 3, 4, 5, 6, 7, 8 chiral centers. So 2 to the 8, which is 256. That is a lot of stereoisomers. And interestingly, out of all of these possibilities, only one occurs in nature. Now, any compound with only one chiral center will be a chiral compound. But if you have more than one chiral center, there is a possibility that the compound may not be chiral because it may have an internal plane of symmetry. So consider these two cyclohexanes, cis and trans 1,2-dimethyl cyclohexane. This compound is chiral, but this compound is not. And that's because there's an internal plane of symmetry. You can cut that right in half, and everything on the right-hand side mirrors everything on the left-hand side. And because of that internal plane of symmetry, that means that it will be superimposable on its mirror image and therefore is not chiral. However, there's no way that you can cut this isomer in half to get the one part of the molecule mirroring the other part. So this trans isomer is chiral. So molecules that have chiral centers and an internal plane of symmetry are called meso compounds. Another way to test if a compound is meso is to see if it's identical to its mirror image. So you can draw the mirror image of the cis isomer and show that it can be superimposed on its mirror image. By definition, when a compound is identical to its mirror image, it is not chiral. It is achiral. Here's an example of some meso compounds. So here we could cut this right down the middle like this, and the top half looks just like the bottom half. Here we could cut this right down the middle here, and this part looks like this half. And here we could cut this right down the middle, and this left side looks exactly like that right side. And meso compounds have less than the predicted number of stereoisomers based on the 2 to the n formula. Now, most methods of separating compounds from one another take advantage of the compound's different physical properties. For example, distillation separates compounds based on different boiling points. Recrystallization separates compounds that have different solubilities and particular solvents. But these methods don't work to separate one enantiomer from its other enantiomer because they have identical physical properties. So when we have a mixture of enantiomers, a 50-50 mixture, that's called a racemic mixture. The term racemate is also used interchangeably with the term racemic mixture. And if you were to take a racemic mixture and test it with a polarimeter, you would find that it does not rotate the plane polarized light. And the reason for this is because one enantiomer rotates the light one direction to a particular degree, and the other enantiomer rotates the light the completely opposite direction but to the same degree. So they just cancel each other out. It can be useful to separate a racemic mixture into its separate enantiomers, a process called resolution. There are a few different ways to do this, and one method is to use a chiral resolving agent. So for example, if I react these two enantiomers with this acid, which is chiral because it has this chiral center and no plane of symmetry, the nitrogen is going to act as the base and it's going to get protonated by the acid. and you'll form the corresponding conjugate acid and conjugate base. So this salt, when you have an ionic compound, you can also call it a salt, is now diastereomeric because this is going to be coordinated with something that is also chiral. So now we have these chiral centers being opposite, but these chiral centers are the same, so the relationship between these salts is a diastereomeric one. Now that we have diastereomers, they do have different physical properties, which allows them to be more easily separated. Chirality is a fundamental property in biochemistry and biology because receptors in our bodies and the active sites of enzymes are chiral and will only accept molecules with a particular configuration. An example of this is when a nerve impulse reaches the synapse, signaling molecules are released that have a particular chirality. These neurotransmitters diffuse across the synaptic gap and bind to receptors, and they bind in a lock and key manner, according to a schematic shown here. And this specific binding prevents other molecules from activating the receptor. So you can see with these different shapes, and this is a very simplistic representation of an active site, only this enantiomer can fit in, not this enantiomer. In some cases, receptors and enzymes will bind both enantiomers, but each one produces a different response. A simple example of this phenomenon is the binding of plus limonene and minus limonene in your olfactory receptors. So this is plus limonene, this is minus limonene. Notice the only difference here is the configuration at that chiral center. Everything else is the same. When the plus limonene binds, you smell oranges, but when the minus limonene binds, you smell lemons. Drugs often also have chiral centers, and one enantiomer can produce the desired effect while the other enantiomer could have a terrible effect. An infamous example of this is that of the drug thalidomide, which in the 1960s was prescribed to pregnant women to help them with morning sickness. So here is the S-thalidomide and the R-thalidomide. The problem was that one of the enantiomers cured morning sickness and the other caused terrible congenital disabilities in the children, including malformed limbs, and many of the children ended up dying whose mothers had been prescribed this. So that was back in the 60s. Now we understand the importance of testing all of the stereoisomers in the body to determine the effects of each one, and any drug that's approved now has to show what each particular stereoisomer does.